Good evening. Welcome everybody to today's talk. The speaker is Professor Shigeto Watanabe of the Hokkaido Information University and Hokkaido University. Professor Watanabe is going to talk about, his original title is called Lithium Cloud Experiment to measure neutral wind in the lower thermosphere. But later on, you will see that he changed the title, but it's almost the same thing. It's about coupling of plasma and atmosphere in the thermosphere or mesosphere. And if you look at his CV, and you'll find that this topic actually is his first love. I asked Professor Watanabe, is that true? And he said, yes, this is his first love. Because he has lately also working on the last 10 years, also worked on Venus. So he is now also a leading expert on Venus, but that would be his second love. And we will not ask him to talk about Venus this time, maybe next time. Professor Watanabe, he got his PhD from Hokkaido University, right, in 1984. And since then, he really spent a lot of his effort on the atmospheric physics. He have published a number of papers, a lot of papers. And he's also very enthusiastic about cooperation, international cooperation, helping different people doing atmospheric science. So atmospheric science. So for in the audience, if some of you have questions to him, please ask him or write to him. You know, if you don't have his email address, write to me, or you could find that on Google and so on and so on. Yeah, Professor Watanabe, please start your talk. Thank you so much.
Thank you very much for very nice introduction. So today's my talk is about rocket experiments. So my first research, original research is ionosphere and thermosphere. After that, we try to carry out the rocket experiments. And after that, Venus spacecraft. So today's, I will talk about the rocket experiments, maybe half an hour or 40 minutes. Okay, so my title is A Coupling of Atmosphere with Plasma, and subtitle is Sounding Rocket Observation in the Mesosphere and Thermosphere. So I am now working in Hokkaido University and Hokkaido Information University, both. So, so many interesting phenomena are occurring in the Earth's atmosphere. So today, I will focus on the boundary layer between the mesosphere and thermosphere. So where plasma is generated and interact with the Earth's neutral atmosphere. So tides, acoustic waves, and gravity waves from the Earth's surface. Okay, now raise a point like that. The waves are breaking and destroying around 100-kilometer altitude. The waves interact with plasmas. However, balloons and satellites cannot observe the region in situ around this region. The waves interact with plasma. So only rockets can observe this region directly. So plasma is present on all solar planets and the atmosphere. So different motions of the ions and electrons generates the currents and electromagnetic field in the lower thermosphere and ionosphere around 100-kilometer altitude. The equation of motion governing this region includes the terms of the ions, electrons, and neutral atmosphere interact with collisions this term. However, the Lorentz force term is also important in the ionized atmosphere. So the ratio of collision and cyclotron frequencies becomes essential for plasma motions. So now the ion and electron motion are different in the region of the Earth's atmosphere around 100 kilometers. So therefore, the currents must be generated. So this region, around 100 kilometers, this region is called the current layer or dynamo region. The altitude width, this width is only 30 kilometers. So key points. A current layer dynamo region exists in the Earth's atmosphere at an altitude of around 100 kilometers. The tidal waves, sound waves, and gravity waves generated at the surface in the troposphere and stratosphere propagate to the mesosphere and lower thermosphere at altitude of around 100 kilometers. And the current layer is strongly affected by these waves. The electric fields generated in the current layer are mapped to higher altitudes and conjugate hemisphere along the geomagnetic field line. So, in order to understand the physics of this region, we decided to use sounding rockets to visualize and simultaneously observe the motions of the atmosphere and plasma in detail. So I will show one example, so which was just published in Nature. So sound waves from the Tonga. Tonga is here. So Tonga volcanic eruption. So reach the ionosphere above. So sound waves reach the ionosphere above Australia. So Tonga eruption is here, and sound waves propagate to Australia. Then electron density fluctuations occurred. So the ionospheric electric field generated here cause the ionospheric electron density fluctuations. And in Japan, at the simultaneously occurs the density fluctuation. So density fluctuation over Australia. So this fluctuation mapped to conjugate hemisphere by electric field. So key points is that the electric fields generated over Australia, so map in the other hemisphere. So plasma bubbles. So plasma bubbles also occurred, which were observed by the Arase satellite here. So this is our satellite electron density. We see many plasma bubbles. So probably the atmospheric waves generated by Tonga volcanic eruption may be seeds of the plasma bubbles. So, so this is some examples of materials so that can be used for visualization of atmosphere, especially atmospheric neutral wind. So these atoms resonantly scatter sunlight in the visible range. So lithium, sodium, magnesium, and calcium, strontium, and barium, and so on. So visualization of neutral atmospheric wind has been done for about 60 years. So in Japan, 60 years ago, we have some rocket experiments. So at that time, they used the sodium, cesium, and barium, then observed those atoms scattering lights of the sun. So, however, detailed analysis was complicated at that time because they use a film camera. So data analysis is so complicated, and detailed measurement of neutral wind was difficult. So from those experiments, we decided to use lithium, so which is easy to handle and observe resonant scattering sunlight from the ground. So we tried many rocket experiments. So we have carried out sounding rocket experiment continuously around the world since 2007. So we launched rocket in the evening, morning, noon, and midnight, and the low, middle, and high latitude. So why we use evening, morning, and the daytime? Because lithium and barium, strontium, those atoms scattered sunlight. So in the upper atmosphere, sunlight still there. So this is the key point one. So in our first rocket experiments, winds, so a lithium canister, plasma, and electromagnetic field instruments were installed on the Japanese S5 to the rocket of JAXA. So launch site is in the Uchinoura Space Center of Japan. So our first rocket experiment is was called by WINDS campaign. So we installed a lithium ejection system. This is a canister, and electric field detector, magnetic field detector, and plasmas, and also waves instruments. So we installed lithium, so totally 390 grams of lithium was loaded in 3 canisters. So these are the cameras. So we used this camera. So camera without the IR cut filter on the ground were used. The optics, this optics with a narrowband filter was also used. So lithium ejection system consists of lithium and thermite by a mixture of ferric oxide and aluminum. So temperature increase to value up to 3000 Kelvin after the ignition. So lithium atoms are released for about 10 seconds for each canister to create a lithium atom trail. So this idea, so at least 10 second lithium burning. So this idea is a new technology developed by us. So the rocket, first rocket was launched from Kyushu Uchinoura town, so towards the southeast direction. So cameras with narrowband pass filter and no IR cut filter were set on 4 ground stations: Shionomisaki, Miyazaki, Uchinoura, and Amami Oshima. The 3 canisters were ignited at altitude of 247 kilometers, 204 kilometers, and 146 kilometers to release lithium atoms into space. Therefore, lithium atom trail was generated from about 100 kilometers up to 200 kilometers or more. So lithium resonantly scatter sunlight. So we launched the rocket in the evening when there was no sunlight on the ground and still sunlight above the ionospheric E region. So this is some examples of taken by our camera. So we named this experiment space fireworks. So the lithium cloud grew more prominent and was observed in many places in Japan, including Uchinora, Miyazaki, Amami, Oshima, and Shionomisaki. So photographs were also taken in Kyoto, very far from Uchinora. So in Taiwan, you probably saw the space fireworks. So lithium clouds diffuse and increase in size with time. So first canics are ignited this time. So altitude 231 kilometer. So time is 1926 local time. Then this lithium atom gas diffuse becomes and also becomes like that. So this is a cross section of lithium cloud. So the cloud is moving by background neutral atmosphere wind because this peak shift to right side. So it's due to background atmospheric neutral wind. So we can estimate the neutral atmosphere wind from cloud shift and the diffusion coefficient from the width change. So this cloud size becomes bigger, larger, bigger with times. From this diffusion, we can estimate some parameters. So now, just we use the simple diffusion equation. So this diffusion equation describes the spread of lithium cloud. The observations and the solutions of this diffusion equation are in good agreement here. So dot is observation data, and this line is a solution of diffusion equation. So from this agreement, we estimate diffusion coefficient, this D. So the diffusion coefficient is shown in the figure on the left. So assuming a lithium temperature, the atmospheric density can be obtained on this profile. So dot is observation data, and green line is by an MSIS model. So we see good agreement, but there is some difference. The difference occurs 220 kilometer altitude. So this boundary is due to N2 to O, N2 molecule density to oxygen atoms density. So probably gradient changed here. So this gradient, so scale height, so we can estimate temperatures, temperature of N2 molecules and temperature of oxygen atoms. So this line is by an MSIS model. So we see good agreements. So next rocket experiments, WINS 2. So this is also was successfully launched. So this wind too released lithium at an altitude of about 100 kilometers along this rocket trajectory. So we launched the rocket in the morning when there was no sunlight on the ground, but sunlight above the ionospheric region. So we obtained the lithium cloud image at 3 ground stations, Tsukumo, Muroto, and also Uchinora. So this is very interesting. So we release the lithium atoms along the rocket trajectory. So trajectory is like a straight line, but that clouds change to these loops because of very strong neutral wind shear exists in the lower thermosphere. So lithium helps estimate neutral wind in the mesosphere and thermosphere. However, it isn't easy to use the triangulation method. So because we do not see any characteristic points, the bright region here and also here and also here is due to the integration effect seen from the camera. So it can be seen that small fluctuation like this, so exists within the large loops. So large loops indicate the presence of neutral atmospheric wind shear, while small fluctuations indicate the presence of atmospheric gravity waves. Okay, so next one, rocket experiments in collaboration with NASA and Clemson University were carried out at Kwajalein in Marshall Islands in 2013 near the magnetic equator. So using NASA Subnig rocket this time. So this experiment was called EBEX, the Equatorial Vortex Experiment. So 2 rockets were used to release lithium with 2 canisters and 2 TMA trimethyl aluminum. So rocket was launched in the evening. So we use 2 rockets. One rocket release lithium gas at altitude of 300 kilometers and 200 kilometers, and another rocket released at TMA, so about 100 kilometers about. So lithium trail. So lithium trail can be seen here. And this trail is bending at low altitude. It shows the presence of neutral atmospheric wind shear as seen in Japan. So here is a TMA. So here is a lithium trail. And so this one, so more over the pictures, first lithium ignited and second one is ignited, and we make a lithium trail to observe wind shear and also estimates the neutral wind. So this rocket was also challenging. So this rocket in collaboration with NASA and Clemson University. So we tried to observe a neutral atmospheric wind during the day. So a rocket experiment with 3 canisters was called out carried out at Wallops in the USA. So we use 3 canisters. First canister L1, so we release lithium gas from 85 kilometer altitude up to 100 kilometer. Second one released lithium atoms 100 to 115 kilometer. So over, we use lithium 3. So during the daytime, the sunlight was scattered strongly in the Earth's atmosphere. So it was challenging to observe lithium cloud from the ground. Therefore, we use airplane. So airplane was used for the observation from an altitude of around 10 kilometers. So 3 canisters were ignited, L1, L2, L3. Then we observed a lithium trail from airplane. So lithium atoms, so finally we release lithium atoms at altitude of 85 kilometer to 130 kilometer. So lithium trail can be seen like this. Then lithium trail changes V shape, and then lithium cloud are like loops. So it takes a few minutes to 10 minutes or 20 minutes. So lithium atoms released along rocket trajectory after 2 minutes, like this. The trail changed V shape, and after 5 minutes, the trail changed a loop. So this image shows the time series of lithium trail from here to like this, and like this, like this. So lithium trail is here, and like this, and here, and V shape changed to loops. These loops bigger and bigger. Okay, in 2013, the rocket experiment was conducted again in Kagoshima, in Japan. So this time, the lithium lights resonantly scattered by the moonlight. So we released lithium atoms in midnight, no sunlight, but still moonlight was there. So, so this experiment by use of moonlight, this is the first time in the world. So lithium clouds were observed from airplane. The neutral atmospheric winds changed the lithium trail. So this is a rocket. So lithium trail is here, and this trail changing and also changing. So this is we plot the lines. So from this picture, lithium trail like this, from this one like that, and here like this. So this time we use also TMA. So TMA also released. So both TMA and also lithium cloud was successfully observed from the ground. So this is from Tanegashima. So we see lithium trail here. So TMA changed over time. So TMA changed over time to now phi shape. It is interesting because of atmospheric neutral wind shear. So neutral atmospheric wind shear is present at altitude of about 80 kilometer and 100 kilometer. So to reproduce this image, so an algorithm was constructed to solve the inverse problem of how the neutral atmospheric wind is structured. So traditionally, triangulation is used to find the atmospheric wind, but the characteristic points from trail-generated lithium cloud and TMA are not accessible. So the inverse problem is an effective method. So we applied this method to wind one, so lithium trail. So it shows the presence of velocity shear with 100 meter per second. So this is wind profile for east-west wind. This is north-south wind. So this is absolute value of wind. So maximum wind velocity was about 100 per second, about 100 kilometer altitude and 150 kilometer altitude. So the same method was applied to daytime dynamo. So this one. So daytime rocket experiment in the USA. So it shows the presence of velocity shear of about 100 kilometer altitude with a velocity with 100 meter per second. So there are small scale. So here, so there are small scale waves on the neutral wind velocity shear. So both nighttime data. So this is nighttime data by use of moonlight in Japan. And this is daytime data in USA, show the velocity shear at altitude between 100 kilometer to 120 kilometer altitude. But these altitude appear to be lower at night. So solving the inverse problem in more detail reveals atmospheric gravity waves associated with neutral atmospheric wind shear. So the measurement error, so now this time wind 2, so measurement error of the atmospheric neutral wind is now about 1 meter per second, like that. So from this image data, we estimate the neutral wind. This is north-south wind. This is east-west wind. So very strong wind shear occurs around 100 kilometer. So maximum wind velocity is about 100 meter per second. And we see small perturbations. This is due to maybe gravity waves. So gravity waves wind is about 10 meter per second or less. So barium and strontium ionize at a specific time constant for tens of seconds. Therefore, neutral atmosphere and the plasma can be visualized simultaneously when barium and strontium are reduced into the space. So Casper experiment we tried were launched into the aurora from Andoya, Norway, to release barium and strontium on 2014. So here is one example of picture. So this is a barium ions, and this is strontium. And another rocket experiments, cusp heating experiments. So was launched from Ny-Ålesund in Svalbard, Norway on December 10, 2019. So 8 barium and 2 strontium were released across the rocket trajectory above 180 kilometer altitude. So next one, cusp region experiment CREX-2 rocket was launched to release barium, strontium, and TMA on 2019. The electric field and neutral atmospheric winds within the aurora are visualized. So another group this year carried out the rocket experiment on March 2023. So now atomic gas released from the rocket in the mesosphere and thermosphere is a common technique to visualize the thermosphere and ionosphere to investigate the coupling process of neutral atmosphere and plasma. Now, just time, summarize. Lithium and barium, strontium help visualize neutral winds and plasma flows in the upper atmosphere. About 25% of lithium installed in the canister was ejected as atoms. So emission intensity of lithium resonance scattering sunlight was about 1 megarad. So illuminated lithium clouds by full moonlight were observed for the first time from airplane and ground sites for a few minutes. So neutral wind distributions were derived in an altitude range from 90 kilometer to 250 kilometer. Strong wind shear was found around 100 kilometer altitude. The velocity is about 100 meters per second. The wind rotates in an anti-clockwise direction with the altitude increase. The wind velocity variation with about 10 meters per second were observed in the velocity shear region. So neutral winds 250 kilometer altitude were almost the same velocity estimated by ion drift observations of mu radar. So large and small scale structures of neutral wind may be due to the tide and atmospheric gravity waves. So neutral density temperature profiles are consistent with the MSIS model, but some difference exists. So neutral density distribution can be estimated from lithium cloud diffusion. So distribution was consistent with MSIS model. There was a density transition from N to O at about 200 kilometers. And finally, some atmospheric waves may be due to the impact of lithium release, and chemical release is a crucial technique for investigating thermosphere and ionosphere coupling. Thank you so much. Just 10 minutes, 40 minutes.
Thank you.
Okay.
Right. So let me ask the audience first. Do you have any questions to Professor Watanabe? And he's one of the, I would say, very few space physicists who could build instrument and do model all at the same time. No. If you could either raise your hands, or write in the chat box. But let me first ask you. Okay, let me see. Yeah, it's just you have any questions? Please write down here or raise your hand. Yes. Let me ask a couple questions first. So in the lithium cloud or barium cloud you the experiment with, sometimes they appear as a cloud, right? Like a rounded shape, right? And then expand.
Yeah.
And then some have a linear structure. Yeah.
Yes.
And some just move around like a fan, as you said.
Yeah.
So does that mean that for the cloud shape, spherical shape situation means that there was no wind at all, or what?
Okay, so lithium atoms are released along the satellite path. So this cloud is just like a bar. So at high altitude, so diffusion is so large. So this cloud expand larger and larger. Then finally, this kind of balloon. So lithium release just along the rocket trajectory, but at high altitude, diffusion is so high. So totally, finally, lithium cloud like balloons. Then, of course, this like this balloon is moving with atmospheric neutral wind. But at low altitude, so low altitude is here. This is high altitude. Here is low altitude. At low altitude, there was a wind shear. Then this trail is bending.
Right. Okay.
Okay.
So it really depends on the wind shear at that time. The other question is that you one time in the 2013 experiment you use airplane at releasing the cloud at 13 kilometer. So my question is that do you think that you can use a drone to do such drones to do such experiment, and then to up to what height in the atmosphere?
Pardon? Sorry,
Drones, you mean the unmanned airplane?
Airplane's data?
You mean using the UVA?
It's a good idea. Maybe yes, maybe yes. So we use two airplanes. One is in USA. So this idea was Prof of NASA Goddard Space Flight Center. So on the ground, so daytime, sunlight was scattering so strongly. So we cannot this kind of cloud because this cloud intensity is only 1 megaradius, but daytime maybe more. But now daytime sunlight scattering is so large. So we use airplane. So about 10 kilometer height, our airplane flies, then take a lithium cloud. So maybe here. So so around here, so dense atmosphere, so maybe cloud or something. So on the more up to the cloud height, then we see lithium trail here. So In Uchinora, we try again airplane by use of moonlight. So in Uchinora, so near the Japan, so town light still there. So it's difficult to observe the lithium cloud. Then we use airplane.
So you use the airplane to observe the cloud, right?
Yes.
Okay.
Daytime and also nighttime.
Mm-hmm. So for the audience who want to know why we still need to, now we have a satellites, you know, in orbit around the Earth. Why do we still need to use a rocket to do the wind measurement? The reason, of course, you know, as you have written to Professor Watanabe,
Yeah.
that you cannot fly a satellite in such a low latitude. So only way you could measure the wind speed or atmospheric composition structure at that height between say 70 to 120, 30 kilometer is to use a rocket. Yeah. I can see the Andre Carabia, Professor Carabia, you have a question, please?
Yeah, no, just a comment. The GO satellite, I think, is flying, is orbiting at 250 kilometers altitude. I think it's one of the lowest, and the International Space Station as well is orbiting very lower. It could be interesting. It could be combining or contrasting the measurements of those satellites, or even to install this technology in small sats also could be interesting.
Certainly, yeah. And you could do, obviously, wind measurement, you know, using CubeSat. Indeed, yeah. There's one places to use CubeSat too. Any other questions? Yeah.
Yeah, very low altitude satellite, maybe so that satellite can measure the neutral wind. But small scale neutral wind is difficult by use of very low altitude satellites, because that satellite velocity was so high, maybe more than 10 kilometers per second.
So, Professor Watanabe, let me ask you the last question.
Okay.
Would you like to have performed such an active experiment in the Venus atmosphere?
So, yesterday we discussing the new spacecraft to Venus. So now we are discussing use balloons in Venus. So this kind of lithium and also another chemical materials is also interesting, but only one. Now, but I'm not sure. But NASA's group, ESA's group, and JAXA's group, and also me. So I discussing how to install the balloons on the spacecraft, then release the balloons, so that balloons observes the Venus atmosphere for at least 1 year or something. And that balloons are changing altitude. So about 50 kilometer up to 70 kilometer, or we don't know.
Very good.
Just discussing yesterday.
And yesterday.
Yesterday.
Okay. So good that you give your talk today. And when do you think you can do that? Tomorrow?
Okay.
That would be a very interesting experiment, mission too, right? That would be the next, maybe 10 years from now, perhaps, right? 10 years from now. Okay, good. Any questions from the audience? If not, I would we would then end the session, and I think it's very interesting. And then the lecture is recorded, so if some of you want to look at it again, and please go to our web page, and you will see that. And so I would want to thank Professor Watanabe again, and we look forward to seeing you in person in Taiwan in October, right? So we arranged that.
Okay, thank you so much.
Thank you very much.
Okay,
Bye-bye.
thank you very much. Bye.